So I haven't done a Leetcode contest in ages, but I figure now is as good a time as any, and we're going to be doing Leetcode Weekly Contest 407. Wish me luck. Last time I did a contest, it was around 200, I think. So we've really come a long way. If you want to check out some of my older videos, there will be a link in the description or somewhere in a card up there. Okay, 3, 2, 1, let's get started. Alright, so let's get started with problem number 1. Number of bit changes to make two integers equal. You are given two positive integers n and k. You can choose any bit in the binary representation of n that is equal to 1 and change it to 0. Return the number of bit changes needed to make n equal to k. If it is impossible, return -1. So essentially we have n and k here, two integers. We're going to represent them in binary and apply a number of operations. For each operation we take a 1 bit in n and we make it a 0. And we need to know the minimum number of these operations needed to convert n to be equal to k. So for example, if n equals 13, the binary representation of 13 is 1, 1, 0, 1, so that's 8 plus 4 plus 1. K equals 4, that's going to be 0, 1, 0, 0, because it's just 4 in this place over here. So to turn n equal to k, we're going to convert these ones into zeros, and that's going to require a total of 2 operations. So this is always going to be possible. The only cases where it's not going to be possible are where n has a 0 in some place where k has a 1. And this is bad because we can't turn zeros into ones, and that's pretty much the only case where we have a no-go. Otherwise, we can turn the 1 into a 0, and that's just simply going to increase the number of operations we need to take. So how do we implement this? Well, we're going to have I, which is our current place value, so it's going to start from 0 for 2 to the 0, and get increase until we get to n. So this operator, this left shift operator, simply means move 1 to the left by I spaces in binary. So essentially 1 left shift I is just 2 to the power of I. So we're going to keep iterating while 2 to the I is less than n, and we're going to check if we have a 1 that needs to be turned into a 0 or a 0 that cannot be turned into a 1. So what this is checking for over here, n and 1 left shift I, is simply checking if n has a 1 bit in the I place value, because 1 left shift I is 2 to the I, and if we AND this, bitwise AND this with n, it's going to be a positive number if there is a 1 in that place value for n. Likewise, we're going to check if there's a 1 in this place value for k, so that's what this is checking. Is there 1 in the I place value of k? If not, then we need to change this current place value, because n has a 1, but k does not, so we're going to need to apply an operation. The other case is if n does not have a 1, so n has a 0 and k has a 1, this makes the entire transformation impossible because we can't turn zeros into 1, so that's going to be a -1 for that case. Otherwise, we're just going to move the place value up by 1 and continue incrementing, and that's how we get our answer. Alright, on to problem 2, vowels game in a string. So Alice and Bob are playing a game on a string. You were given a string S. Alice and Bob will take turns playing the following game where Alice starts first. On Alice's turn, she has to remove any non-empty substring from S that contains an odd number of vowels. So we have this string S, we can take any substring from it. Has to be non-empty though, that contains an odd number of vowels. On Bob's turn, he has to remove any non-empty substring from S that contains an even number of vowels. The first player who cannot make a move on their turn loses the game. We assume that both Alice and Bob play optimally. So return true if Alice wins and false otherwise. So this problem for me was kind of tricky, mostly because it was simpler than I thought it was. I tried doing a dynamic programming approach, but then I realized it wasn't really necessary after thinking about small cases. So it turns out what we really care about here is the parity of the number of vowels inside S. And here's what I mean. I claim that Alice wins so long as there is at least 1 vowel inside S. Why? Well, if S has no vowels at all, Alice goes first, can't do anything, so she loses. But if there's at least 1 vowel, there's either an odd number or an even number of vowels inside S. So an odd number of vowels, for example, we can have F, F, B, P, O, and then some other vowels like L. I'm looking at my keyboard here. N, M. So there's only 1 vowel inside the entire string, or there's an odd number. Say we have like maybe an A and an E over here. What matters is that there's an odd number. What Alice can do is just remove the entire string, because the entire string is a valid non-empty substring of S that contains all of the vowels. What Alice can do if there's an even number of vowels, so say there's like, we got this string, except maybe there's another vowel over here like an I, so there's an even number, in this case that's 4. What Alice can do is remove everything except for one vowel, and you can always do this because you can always just cut off the last vowel, for example. Remove everything but one vowel. In that case, the remaining string has only one vowel left, and Bob can't do anything because he has to remove an even number of vowels, but there's only one left, and you cannot remove 0 vowels. So Bob is in a pretty tight position there and loses the game because he can't do anything. So all we need to do is count up the number of vowels in S, and what I did here is just a simple for loop, go through all of the characters in S, and increment our count of vowels by 1 if the current character is within the string A, E, I, O, U, so just checking if the current character is a vowel. Once we have the number of vowels, as long as there's at least one vowel, Alice wins because she can use the strategy that we just talked about. And that's pretty much it for problem 2. Alright, on to problem 3, maximum number of operations to move ones to the end. You are given a binary string S. You can perform the following operation on the string any number of times. Choose any index I from the string where I plus 1 is less than s.length, such that s of I equals 1 and s of s plus 1 equals 0. So essentially what this means here is we take any index such that this current index is 1 and the next one is 0, move the character si to the right until it reaches the end of the string or another 1. So for example, if s equals 0, 1, 0, 0, 1, 0, we can choose I equals 1, that is this one over here. You can see it's valid because the next character is a 0. We move it all the way to the right until it hits a 1 or it hits the end. In this case, it hits a 1, and the resulting string is 0, 0, 0, 1, 1, 0. What we have to do is return the maximum number of operations that we can perform. So we're doing a greedy strategy here. We want to move the ones to the right as much as possible and return the number of times that we can shift these ones. So let's start off with analyzing an example. We have 1, 0, 0, 1, 1, 0, 1. Now in this case we can make 4 total shifts. I think it turns out the answer is the same no matter what order you choose. And I'm sure there's some way you can prove this, but based on the phrasing of the problem, you can kind of assume that's the case. So the order we're going to choose is from left to right, essentially. Our algorithm is as follows. You start at the left and find the first one. Check if there's a gap of zeros that you can slide to the right over. So for our example, we have this one and we can slide it over this group of 2 zeros. And the number of operations we can get with this gap is actually the number of ones that we've seen so far. And then number 4, slide to next one and go back to step 2. So in this case, we have just one slide operation. This first one is going to go over to the right like that. We're going to move on to our next one, check for a gap of zeros. There's no gap of zeros. Go to the next one, check for a gap of zeros, and there is one. So this 0 can actually be used 3 different times, once for each of the ones that we've seen so far. And the reason we can do that is for every one, we slide it to the right, so that one can get slid over. Once it gets slid over, the gap now transfers to the left for the remaining ones on the left to be used. So we can slide this one over as well, and finally slide that leftmost one over. So we got 3 uses out of that gap, and that's why we add the number of ones seen so far. And the code for this is actually relatively short. All we need to keep track of is our current location, the number of ones seen so far, and the answer, which is the maximum number of operations that we can perform. So we start off with our current index at 0, and we're going to move it through the string, processing the number of operations that we can make. So if we're currently at a 1, then we're going to increase the number of ones we've seen by 1. We're going to shift to the right until we hit another 1. So we're going to create this new variable called j. It's going to represent the index as we seek forward. J is going to be I plus 1, so it's going to be 1 index ahead. We're going to keep incrementing it while we're over the zeros, and eventually we're going to either hit a 1 or we're going to hit the end of the string. So now we have this sort of gap of zeros, and once we hit either another 1 or the end, then we can increment the number of operations by the number of ones we've seen, because the gap can be used a number of times equal to the number of ones we've seen, as discussed. And then after that, we just shift our current index over the gap to the next one or to the end, and that's pretty much it for problem 3. It's more or less a one-pointed problem. You're sliding it over the string, keeping track of various variables in our computation of the answer. Alright, and now it's time for problem 4, the most difficult of them all. Minimum operations to make array equal to target. You were given 2 positive integer arrays, nums and target, of the same length. In a single operation, you can select any subarray of nums and increment or decrement each element within that subarray by 1. Return the minimum number of operations required to make nums equal to the array target. But essentially what we're going to do here is we're going to track the deltas between every element in nums and try to make this equal to target instead of applying all these operations because it's simpler. So let's talk about what I mean. So our example array in this case is 3, 5, 1, 2, and I like to represent this actually with a bar chart. So we have 3, 5, 1, 2, and we want to try to make this equal to 4, 6, 2, 4. So we got here 3, 5, 1, 2. The deltas are the sort of hops we need to make between each of the elements. So we need to hop +3 at the beginning, then +2, then -4, and +1. So the delta array is going to look like 3, 2, -4, 1. And for the target array, it's going to be +4, +2, -4, +2. Now notice there are some similarities between these two arrays. In particular, this 2 minus 4 is preserved between our original array and the target. And what this means is we can actually preserve this structure as we do operations. So we've got this 3, 5, 1 here and this 4, 6, 2, and the deltas here are 2 minus 4. The great thing is in an operation, in just one operation, we can change all of these three numbers to be matching with the target. So 3, 5, 1, if we add 1 to all of them, which is allowed by the operation, we get into the target, and this is reflected by the delta arrays having the same two numbers in these locations. Because the idea is we're sort of like raising this level by 1, right? We're just adding one level to these first 3 bars, and that's going to preserve the shifts between the bars that we see. So just take a maybe slightly bigger example. We're gonna say 1, 2, 3, 4, 5, 6. Suppose we want to make this equal to 1, 3, 4, 5, 5, 6. Just kidding, that's a 6, 6, so I'm going to cover it up with a little overlay. So this is very crude, not to scale, but we can do this in just one operation, and that's by raising these 4 bars up by 1. So that's selecting this subarray and increasing it by 1. That's just one operation, and it's going to get us to our target array. Now in terms of deltas, the original delta array is going to look like 1, 1, 1, 1, 1, 1. And the resulting array looks like 2, 1, 1, 1, 1, 0. Now notice what we did here is we raised these middle 4 bars, and the corresponding operation in the delta array is going to be +1 to this first element and -1 to this last element. And what's happening here is that between the first and the second bar, we're giving the second bar sort of a boost, so that's what this +1 is for. And this +1 carries over into the next 4 indices, but we don't want it to carry over into any of the following indices, and that's why we have this -1 over here, so that after we give the boost, we level it out. So to summarize, we have a delta array both for our nums array and for our target array, and we want to make these two delta arrays match, because if they match, then the original arrays will also match. Delta array, again, is just the changes between consecutive elements in the original array, and the operations in the original array correspond to bumping one element up by 1 in the delta array and a corresponding one down. So one operation we could have is bumping up the 3rd index up by 1 and bumping up the 7th index down by 1, and that corresponds to making these indices higher by 1 height. Alternatively, we can bump some stuff down at the beginning and bump it up at the end, and what that corresponds to is bumping this entire chunk down by 1. Now notice if we have an operation that ends at the end of the array, then we might not actually have 2 numbers here. So these are 2 example operations. Another operation we could have is just +1 over here for the delta array, and what that does is it makes all of the elements from here to the end increase by 1. You can do it similarly for -1, that just bumps all of these down by 1. So we don't actually need 2 numbers to be changed in one operation for the delta array. So let's do an example. Let's actually go with example 2 over here. It's going to be more illustrative. Nums is 1, 3, 2, target is 2, 1, 4. So here's the original array and here's the delta. Looks like 1, 3 is increase of 2, 2 is a decrease of 1. Here, 2, decrease of 1, increase of 3. To make delta equal to target, for the first element, we're going to have to increase that by 1. The second element, we're going to have to decrease that by 3, and the last element, we're going to have to increase that by 4. Now, the great thing about operations in this problem is that they come 2 at a time. We don't only have to apply changes to one element at a time. We can have a +1 and a -1 in different places in the array. So instead of doing +1, -1, -1, -1, +1, +1, +1, +1 here to make the changes to the original delta array for a total of 8, what we can do is consolidate some of those. So this -3 and this +4, we can sort of pair up their operations. We can do a minus here and a plus there, minus plus, minus plus, and then we sort of get into the solo operations. So this one gets a +1, and then finally this +1 at the beginning needs to be taken care of, and that's only a total of 1, 2, 3, 4 operations. So the question is, how do we compute the best way to pair them up? So the way I thought of was to categorize the delta changes by positive and negative. So we're going to have positive changes here and negative changes here. So positive changes, there's a +1 needed at index 0. write the indices here. There's a -3 needed for neg here. We're not going to keep track of signs since we know which are positive and which are negative. Finally, there's a 4 here needed in index 2. So you have to decide an arbitrary cutting point, let's say over here, and then all the positive operations on the left side of the cutting line are going to be paired up with the negative operations on the right side of the line, and all of the positive operations on the right side of the line are going to be paired up with the negative operations on the left side of the line. So these are going to happen in tandem, and these are going to happen in tandem. Now, of course, we can't get this cut perfectly right, so some of the numbers are not going to match, but what matters is that we can sort of cover some of the operations with the other ones to reduce our overall operation cost. For example, making this cut over here is great because we need to make 4 plus changes on the right side and 3 minus changes on the left side, but this will only require 4 changes because for 3 of the changes we can pair up the negatives with the positives, and for the final one we'll just see the positive one alone. So in a bigger example, we're going to have our positives over here and our negatives over here and our indices just labeled along the top like so. We want to find an optimal cutting point, let's say over here, such that this and this, the maximum of that is the number of operations we make for this combination, and this, the maximum of this and this. Once you add these two maximums together, you get the minimum amount. So how do you implement this? Well, we're just going to scan through the entire array, basically. Consider every single cutting point, look at what the maximum of these plus the maximum of these is, and then basically keep track of what the minimum of all of those is. How do you do that efficiently? Well, you can use prefix sums, which is really funny. Prefix sums are coming back to haunt us. But prefix sums are going to let us compute all of these sums in one time, since the positive and negative arrays are going to be static, so we can pre-compute those. Great, so in terms of implementation, so we got this function over here that computes the delta array for any given array. All it's going to do is start with 0, and then every element is going to be the difference of the current element and the previous element. So this computes how much the array changes over time. We're going to compute the delta arrays for both nums and target. We want to make dn equal to dt. That's going to ensure nums is equal to target at the end, of course. So d over here is going to keep track of what changes we want to make dn equal to dt. And maybe the sign should be flipped over here, because that's what I did in my explanation. But in the end, you'll see it doesn't really matter. So we got pos and neg, which track the number of +1 operations and -1 operations we need at every index, respectively. Over here, I skipped over some of the implementation details. These are actually going to be prefix sum arrays, not the actual pos and neg arrays, just to make computation a little bit easier. And over here, we got total pos and total neg, which is just the final elements in these arrays. And that's going to help us compute some of the suffix sums, because, for example, this red sum over here, we can't compute that with the prefix sum. We're just going to do the total of the positive array minus this green sum over here, because the total of these two has to equal the final element in pos, which is actually prefix sum. So we're going to keep track of our answer as we loop through finding the optimal cutting point. I honestly don't know why I set it to maximum of total pos and total neg. I don't think that's correct, but it worked. So actually this should be something like just a really big number, I think. Never mind, that didn't work. So I guess we do need the maximum of the... I don't know what I was thinking. Oh, okay, this makes sense, because we can't have any index have both a non-zero entry for pos and a non-zero entry for neg, because that would mean we want to both increase and decrease the current index for the delta array, and that doesn't make sense. So if you take the maximum of these two, it's basically doing this maximum business in a very concise way, because it's basically taking the cutting point to be the very last element over here. So we're taking this positive operation with all of these negative operations, and this negative operation with all of these positive operations. So pairing those up and then seeing which of those has the most operations needed. It's a little bit shady, but it works out, so we're not going to complain. So we're going to loop through the entire array looking for the optimal cutting point. And so, for example, if I is at 3, then we're going to take our greens, which is positive, or I guess the prefix sum of positive up until 3, so you can see that's this right here, plus the counterpart, which is the number of negative operations on the other side. And that's going to be the total number of negative operations minus the prefix sum of the negative operations up to this point. And then the other part, the red part, is equal to the maximum of the number of negative operations up to this point, that's this red over here, plus the total number of positive operations minus the prefix sum of the positive operation, which is just the number of positive operations to the right of the cut. And we're doing with that with a suffix sum, which is really a prefix sum in disguise. Once we've looped through the entire array looking for optimal cutting point, we will have found 1, which is the best, and that's our answer. So that's it for problem 4. doing this kind of delta array prefix sum thing is a paradigm that I've seen in a number of problems past, so that's how I was able to sort of recognize it. But if there's ever a problem that involves, say, increasing a batch or a contiguous subarray of a given array by constant amounts or decreasing it by a constant amount, I always think about prefix sums, or rather delta arrays, which are the inverse of prefix sums, because instead of operating on whole ranges, that only involves operating on two distinct points, raising one and decreasing the other by the same amount. For the delta array, which has the same impact as changing that range by a constant value for the original array. So that's it for problem 4. So overall, this contest, pretty good contest, lots of operations type problems. So that's it for the explanations. As usual, if you have any questions, feel free to drop them down in the comments below. I'll do my best to respond, and that's it. Thanks for watching. I'll see you in the next one.